Thank you for inviting me. Today, I will present one of many current fintech projects that I'm working at Aboitis. Today, we'll be focused on generating synthetic data for banking applications. So in this talk, I will discuss the need for synthetic data. I would walk through generally our approach to generating synthetic data. How do we assess the algorithms? What are the possible banking applications? Of course, I would touch on some challenges that still remain even with synthetic data. And I would very briefly touch on the future direction we'll be undertaking for this work. Okay. So banks require data for analytics, and currently there are a lot of AI models that drives a lot of operations within the bank, but training AI models obviously require large amounts of data. And unfortunately, financial data is complex, is hard to obtain, and is heavily regulated. So data sharing with other financial institutes is also a challenge. So, however, what we think is that synthetic data generation is actually a good solution in trying to meet these challenges. All right, so what I would show in the later slides is our approach to generating high quality, accurate synthetic data. So what is the use of data in financial services? So banks require data for risk assessment, fraud detection, customer services, and personalized services. So the banks actually need large amounts of high quality data for training and deployment of AI models in the banking sector. The banks also require accurate data, mainly for reporting and for auditing purposes. So they need a lot of data to meet regulatory compliance and reporting. However, of course, this is challenging to achieve, again, due to the complexity of financial data and strict regulations. So first of all, privacy laws like GDPR and PDPA, they actually limit how data is being shared. So banks just cannot share data with other financial institutions or even to external partners. Secondly, security risk is an issue. Financial data is extremely sensitive. So if it falls into the wrong hands, it can be misused for fraud, for identity theft. Thirdly, high quality data is actually very scarce. I mean, yes, there is data, and even when it's available, it may not be labeled properly. There may be incomplete or missing data, or it could be just ingested incorrectly. So this is also an issue. Lastly, we need to talk about bias. For example, if past decisions overlook a certain or specific groups of people, such that, let's say, a certain group of people has been denied loans compared to other groups of people, what happens is that the AI models would sort of learn these kind of patterns and then sort of repeat the same unfair patterns. So these challenges actually make real financial data very tricky to work with. So obviously the next question is then why do we need synthetic data? Well, first of all, we need better and more robust AI models. So more data means more accurate and more robust AI. Another one, like I mentioned, was a fairer AI. It balances data sets and preventing bias, and therefore we can actually have better predictions. The third point is safe data sharing. So banks and external partners can now collaborate with sharing data without exposing real customer information. Another point is that it saves time and money. So there's no need now for you to wait for approvals to get data. There is also no need for you to go out and collect large amounts of data for your AI models or for your analytics. Now, there's one point that has not really been discussed very often, and that's it accelerates innovation, because now developers, data scientists can test and freely test new ideas because they now have access to high quality synthetic data. So in short, in summary, synthetic data actually removes a lot of these barriers to allow banks to have access to high quality data that they can use, mainly to drive decision making and also to drive innovation. So I'll go through our general approach in developing synthetic data. First of all, before any development or any testing of our algorithms, it was essential that we conduct a literature review to find the most effective, robust, and scalar approach within the financial domain. So our first goal, as seen here, systematic review, is to identify the literature that we were going to review. To do this, we follow the Prisma methodology, which is not part of this presentation. But basically what Prisma does, it ensures transparency and reproducibility to ensure that we can collect, assess, and synthesize our literature. The reason is because we want to build algorithms, or we want to test our algorithms based on evidence rather than assumption. So we actually refer to literature for that. Beyond identifying algorithms, we also took a closer look to the benchmarks, performance matrices, on how the researchers in the literature, how do they assess the model that they developed or they tested. So this will help us to also come up with our own benchmarks in determining how we want to assess our own tools and algorithms. So I would go through the first part, which is the identification of the algorithms. So what do we find in our literature review? So we actually group the algorithms into two. One is GAN-based, and the other is non-GAN-based algorithm. So GANs, the generative adversarial networks developed by Goodfellow, is actually traditionally been the leading approach in generating synthetic data. Up to, I think, 70% of the literature actually use GANs. But what we also found was more recently, post 2023, a lot of methods have sort of shifted to other alternatives, such as non-GAN-based algorithm. So I will quickly touch on these two different ones. So first one is the GAN-based algorithm. Just a quick overview, what are GANs? So GANs consist of two neural networks. One is the generator that creates synthetic data, and one is the discriminator that tells it whether it's real or fake. So why GANs? Well, first of all, it's a very powerful tool for high dimensional realistic data generation. So they can actually produce data that's very complex, which means that it's very, very suitable and useful for financial data. Another good point for using GANs is their ability to produce outputs that have similar statistical properties of real financial data. So these are the good points. However, standard GANs are they're very difficult to train, and they have issues with generating very diverse results. So obviously there have been extensions and advancements to GANs, So what we also tested on is the Wasserstein guns. I think 28% of the papers review actually use WGAN with a bit of modification. So what WGAN does is that it solves the problem by using Wasserstein distance. So it is actually one of the methods used to compare the differences between real and the synthetic data. So what it does is, because it's more stable, you actually have more stable training. And because it's more stable, you also do not have outputs that are constantly repetitive. So that is one main advantage of WGANs. The other point is it also reduces what we call mode collapse. What mode collapse means that it gets stuck by producing only a few variations instead of the full possibilities. So I think this generally happens because the generator finds a shortcut and manages to fool the discriminator. So that's what it does, is it prevents a mode collapse, or it reduces the mode collapse. Another point is that WGANs has a critic. So what it does, it actually produces a score to help the model train better, rather than just having a discriminator says whether it's real or fake. So in general, this approach results in more stable training, better outputs, more diverse synthetic data. Another modification is what the CT guns, or conditional tabular guns. It's a more advanced version because it allows you to create data based on certain conditions. So if you have control issues, this would be really, really good, because what it does is you can specify the condition. How does it work? So this is the conditional generator. What you do is you pass a condition to the input, and the generated sample will fulfill the condition, which is then being assessed by the discriminator. So what this means is, for example, you want to create customer profiles of a certain age, specific income levels, spending habits. This is CT guns is what you would use. So in simple terms, this is a tool you use to generate customized financial data, like specific customers or stocks. This is basically it. Now, doppelganger. Doppelganger, or D guns, is another special type of guns. This actually is sort of like a smarter approach because it actually separates the entire process when looking at data. So first of all, it separates the data based on whether it's time-based or any metadata distribution. Then what it does is it normalizes the data. You can do a min-max, for example, for better consistency. What it does is it actually prevents mode collapse, which, again, as I mentioned previously, mode collapse is when the model generates a very limited set of data instead of the whole range of possibilities. So this is what it does for when it comes to normalizing the data. And then what it does is it actually does a batch generation. So what it does is it creates multiple samples at once, rather than one data point at each time. So what it does is this model allows you to recognize time-based data. It allows you to recognize events that occur over time. And what it allows you to do is analyze temporal correlations. So it makes it very useful to generate synthetic data. So now we will go to the non-GAN-based architectures, mainly the autoencoders and the diffusion models. For autoencoders, imagine you have a lot of data, for example, like stock prices or financial transactions. So autoencoders actually is a type of model that helps us to understand and predict time-based data. So it works like this. Firstly, you take a series of data points and then you compress it into a smaller, lower dimensional form of data. You can recognize the distribution. Distribution could be in mean or variance. It's in simple form. And then the decoder gets the distribution and try to recreate the data. And this process is repeated. So it's repeated until your data is of good quality. Now, what makes autoencoders so special is that it just doesn't look at data point by point again. It looks at data, what happens before and after. Therefore, it's very useful if you are analyzing or you want to spot anomalies or outliers. So this is a tool you would use. Another thing that is very, very special about autoencoders is it actually handles missing data, which is, like I said, does happen in real financial data. So if you have missing data, the autoencoders can work with incomplete data and can also work with data that does not have labels. So this is the main point. Diffusion type of model, again, is another type of non-GAN-based algorithm. What it does is it gradually generates noise, and then it transforms into structured data over time. For example, in the first step, you have a blurry picture, and then as you go step by step, the picture becomes clearer and sharper. So that's what diffusion models do. So in simple terms, the model begins with random noise, and then at each step during training, the FinDiff learns how to perform this transformation that will match the characteristics of real data. Obviously, as you can see, it takes a lot of steps. So it could be computationally intensive. FinDiff has a huge advantage because it can handle mixed data types. Now, financial data is actually of mixed data types. So you can have categorical data, such as names, the bank that you just sent your money to. So that's categorical. You can also have numerical data, which is obvious. The amounts of money, that's numerical. So what FinDiff does is it can actually handle the mixed data types simultaneously, right? As I mentioned with GANs, there's a problem with training stability and mode collapse. FinDiff doesn't have this issue. The other thing that FinDiff excel in is that if you have a smaller data set or imbalanced data set, the diffusion model will work just as well compared to, let's say, GANs, which require a large amount of data set. So in summary, the key idea behind GANs is that it uses two models, a generator and a discriminator, one that judges whether it's real or fake. The two models compete with each other. The advantage is that it can create high quality, realistic data generation. Unfortunately, as I mentioned, there's a lot of training instability and mode collapse. The other one is autoencoders. As mentioned, autoencoders work by encoding data into a compressed data set and then try to generate new data. So it's very efficient, it's very stable. Unfortunately, the data generated might not be as good as GANs. As mentioned in the last slide, diffusion models is excellent if you have mixed data types, and it's more stable than GANs. Unfortunately, because it might take a lot of steps to learn the real characteristics of real data, it might be computationally intensive compared to the autoencoders. So this is the summary of all the models that we were looking at from literature. So this is the second part. as I mentioned, from the literature as well, we try to come up with our own benchmarks and performance metrics so that we can assess the performance of the models, the algorithms, correct. So we came up with a few metrics to evaluate the effectiveness of our algorithm. First one is fidelity. So this basically measures how closely the distribution of the synthetic data is similar or not to the distribution of the real data. We use what we call a KS statistic, which compares, like I said, the distribution. We also use Pearson correlation. What it does, it just checks how well the relationships between the variables in the synthetic data and how it will align with the real data. The next is synthesis. Now, what synthesis does is it gauges how well the model create unique data set. You do not want the model to sort of memorize real data. So how unique it is, how creative it is. So what we did was for every generated data point, we check if there is another value in the real data that falls within 1% of its value. So that's synthesis. Efficiency. What we do in efficiency is we ran the algorithm 30 times and we take the average time per second. What we did was we took the average, we took 100,000 original data sets and then tried to generate another 10,000 synthetic records. We run it 30 times and we take the average time in second. Why do we do this? It helps us to understand how well the model performs computationally. It helps us to understand what resources we need when we have to deploy the model in business units. And basically gives us an understanding of balance between complexity and of course, practicality. Okay. This, as I mentioned, is a very important point. This ensures that the generated data doesn't pose any re-identification risk. We use what we call a DCR or an NDR. What DCR does is we take each point in the synthetic record, we try to find the next closest point in the original record, and then we measure this distance. Now, if the distance is very small, chances are it might be a copy, all right? NDR, as the name suggests, is called nearest neighbor. So instead of finding one record, we find two records and calculate the ratio. So again, if you have a very small ratio, it means that the point and its neighbors could also be a copy. So this is the privacy score. Last one is graph metrics. So in financial data, we have a lot of connectivity. So for example, some transactions are more common, or happens more frequently than others. So this is what a network is. So basically we use what we call a net simile score to compare the connectivity patterns between the synthetic data and the real data. We just want to understand whether the algorithm could replicate the relationship of the real data. So this is the graph metric. So what did we find? The green just means it's very good or high scores, or it's the best score. Red just means it's very poor scores. And this is just a very condensed summary of what we found. So very quickly, for GAN-based algorithm like doppelganger, D-GANs, they're excellent at recognizing and capturing complex patterns. It's very good at creating high quality data. However, it's not very efficient. So they have a very long training time. On the other hand, we have non-GAN-based algorithms like autoencoders or diffusion models. As you're aware, their approaches are more probabilistic, they use statistical methods to generate synthetic data. And because of that, they could mimic a lot of the data of the original data. But then the problem is they have very low privacy scores. So I think what I want to show you in this table is that if you want to use it for a business unit or you want to use it for a specific use case, a lot of it depends on how you want to do a trade-off between privacy, security, and effectiveness. All right. So in summary, this is what we found. GAN algorithms in general require more training time. Doppelganger perform the best in data novelty and privacy. Autoencoders and diffusion models have the ability to preserve the statistical distribution of the original data, but in so doing, they actually pose privacy risk. All right. Unfortunately, none of the algorithms could replicate the connectivity patterns or the relationships in the real data. So how can then this be applied to banking use case? First of all, what we suggest is for privacy cases or when privacy is concerned, doppelganger might actually be the go-to case. So this is just one example. For example, if the banks want to share synthetic data with another fintech company to build better credit scoring models, what we recommend is that you can use doppelganger to generate synthetic data or any customer data. And instead of sharing the real data, now you can share the synthetic data. So then the fintech company can analyze synthetic data, test new algorithms, and maybe create better models. All right, so this is one example. This also applies to academic collaborations, which we have, and also with external partners. So what we recommend is to use doppelganger, for example, if you work with academic partners to look at consumer behavior, economic trends, doppelganger would be the way to go. And all this is done without actually revealing any real information about your customers. Another example is scenario testing. So this is just an example. So if the bank wants to understand or test a scenario, like what will happen if there's a sudden increase in interest rates, and let's say we don't have access or we do not have quick access to certain data. So what we also recommend is that you can test it first using doppelganger to generate the synthetic copies of the customer data. In which case then we can use the synthetic data to understand how various interest rates would impact, let's say, default rates, repayments, and obviously how much profits we'll be making. So this is actually another example of when we have privacy issues, we would use doppelganger. On the other hand, you have the non-GAN-based algorithms like autoencoders and diffusion models. This is more straightforward. You can use it for a lot of use case that maybe privacy is not an issue. Common use cases are, for example, like fraud protection, as I mentioned. So let's say you have a data set where fraudulent transactions is very small compares to non-fraudulent transactions. So you have an imbalanced data set. And what happens is that AI models do not really train well on that. So what you can use is you can use an autoencoder to increase the samples of fraudulent transactions in your training data set. And this makes it better for AI models to have better predictions. You can use it to identify individuals likely to commit fraud, right? Yeah, so this is another really special use case. I think in a lot of data sets you use, you have a lot of demographics, you have a lot of attributes in your data set. For example, gender, you could have an imbalanced attribute. Maybe housing, where do you stay, income levels, maybe. So you have, let's say, a multi-label system. You have a multiple labels, they're all imbalanced. So what do you do? So in such a case, AI models training on these imbalanced data set would just give you an unfair or a biased prediction. So what we recommend is that you can use autoencoders or diffusion models to generate synthetic copies of those imbalanced attributes. And what it does is what happens is that the AI now can train on more diverse and more representative data. So this is a use case. So in summary, again, this is back to the very colorful table. Depending on your use case, right? The selected algorithm has to lead to better data-driven decisions and, well, innovation, for the bank. Nonetheless, despite the use of synthetic data, obviously there are challenges and other considerations. First of all, it's very important to remember that real-world data changes. So if you're going to have a synthetic data that is not representative of, let's say, your current customers, than what you have like a year before, then obviously you're not going to have very good prediction or data-driven decisions. So what this means is that we still need to regularly validate and update the data that you synthetically generated. Another concern is the risk of misuse. Now, synthetic data, yes, though designed to protect privacy, could still be manipulated, could still be misused. So what this means that strong data governance should still remain in place, even with the use of synthetic data. Next is transparency and explainability. Now, synthetic data alone doesn't make AI models more explainable. So it's still crucial that when you're using AI models and we're using synthetic data, you still need to justify your decision and you still need to explain the decision that the AI is making. So this accountability ensures trust in the system that you're using. Yeah, so lastly, it's trust. Now, obviously, a lot of these synthetic data is used by business units. So you need to ensure there's clear communication to the business units. You need to ensure that there's confidence in the tools used, even though they're using synthetic data. So this will ensure that it will help all your business units understand what is being used for. So this is, so despite the use of synthetic data, you still need to ensure that this is being clearly communicated to your business units. Nonetheless, we have also found gaps in our current models, and the current models do not fully capture time dependencies, and like I mentioned, graph structure or the connectivity issues. So transactions are not just a one-time event. Sometimes it happens a lot, and it really depends on personal habits, preferences. You might spend more during Christmas than other parts of the year. So basically, if the generate data does not account for these patterns or for these shifts, then it actually will miss important predictions or events. The other challenge is understanding how different data points are correlated or interconnected with each other. So pretend it's like a social network, right? You have friends, you have families, you have classmates and coworkers. Sometimes you're closer or you to one person than the other. So similar to financial data transactions, you may have some transactions happen more frequently with certain accounts rather than other accounts. So this is a graph network. And so what happens is that if the model cannot replicate the relationships in the real data, what happened as well is you're going to miss a lot of connections, and you're going to lose a lot of potential because you can cross-sell. Also, like I said, fraud detection. Fraud detection is also a network. So you'll miss all those important predictions. So what this means is there's a lot of room to improve, and this is actually our current work to have an algorithm that simultaneously and can replicate both time-based and graph connections. So to recap, in banking and finance, data is essential, mainly because we need to ensure that it's privacy preserving, and we need to make sure that it's available because of these challenges. And as mentioned, GAN-based algorithms, they're very good at capturing complex financial distribution, but it has training instability and mode collapse, while non-GAN-based algorithms, they're more stable, they're more efficient, but then they're not very good with privacy scores. So again, doppelganger is the best choice for privacy-preserving applications, while autoencoders and diffusion models are probably are better for data augmentation, or if you want to handle imbalanced data sets. And this is the paper that we published. If you want more details, you can refer to the paper. And thank you.